on Friday, okay, we learned about how gravity can provide a centripetal force and how you can get something into orbit provided you can make it travel fast enough that the distance the Earth curves away is accounted for by the distance the satellite falls or vice versa. Okay? So in this one, they've got a couple of tricks that they're trying to play on here. Okay? The first trick is they give you the altitude. What do we need in a calculation like this? We need radius, which is measured from center to center. So I've got to take this 912 kilometers that they gave me, convert it to meters, because that was the other trick. Okay, they gave it to you in kilometers, and it's useless to you that way. So you got to convert it to meters, and then you have to add the Earth's radius to that in order to get the actual orbital radius of the Landsat satellite. Everyone follow what I'm doing there? Okay, radius is always measured from center to center. So, and I think I mentioned this on Friday, okay, but it orbits the Earth at a height of this, okay, or at an altitude of this, or it's this far above the surface. Any of those are keywords that you were not, in fact, given the radius.
So on the board, it says that the average radius of the Earth is 6.38, but the formula sheet says 6.37.
Oh, here, it does say that. Okay,
so should we trust the formula
Trust
sheet?
the formula sheet always.
Okay.
Yeah, for some reason this book is 1 decimal place off on everything. It's 1 decimal place off on the mass of the Earth. It's 1 decimal place off on the radius of the Earth. It's 1 decimal off on the mass of the moon and the Earth-Moon radius. The only one it's right about is the average Earth-Sun distance, and I'm sure that was just a rounding error we didn't catch because it was far enough back, okay, that it's not shown. Yeah, I don't know why that is. The one that we get is updated every year, and it's always these numbers. So we're going to go with the formula sheet. Okay, the book is getting old now. Yeah, it's actually. If any of you had Mr. Antonuchin for a teacher, his father-in-law wrote the textbook. Yeah, true story. Small world, right? 6 degrees of separation. Okay, so we've got the radius after we calculate it, of course. So we're going to take our 6.37. E6, and we are going to add to that 912,000 kilometers. Okay, so we've got now a radius of 7.282 times 10 to the 6. All right, so we've got that now, and we've got the radius of the Earth, which it doesn't really, it's not going to change your answer hugely to have the 6.38. Okay, but now we can do this calculation here. So we're going to have mv squared over r equals big G times the mass of the Earth times the mass of the satellite divided by r squared, and this over here is also the mass of the satellite. So what's going to happen to the mass of the satellite? It's going to cancel. All right, we're looking for v. So I'm going to multiply both sides by r. R will cancel off the square. And then I'm going to square root to get v. So v is going to equal the square root of 6.67 times 10 to the minus 11, that gravitational constant, times 5.98 times 10 to the 24, the mass of the Earth, okay, divided by our radius, which 6.37 times 10 to the 6. Okay. So when we do all that, whoops, you're right. Nice catch. Who was that? Good catch. Better. And then I got to square root that. All right, so it's moving at 7,400 meters per second in its orbit, which is pretty fast. And it's almost that 8 kilometers per second number Newton figured out for, being close to the Earth. Okay, so we've got that number now. Can I calculate the period? Yeah, and I don't have to do substitution. If I calculated v first, all I have to do is go v equals 2 pi r over t, okay, and solve for t. So t will be 2 times pi times 7,400, okay, divided by, no, sorry, 7.282. 7.282 times 10 to the 6 divided by 7,400. Okay, and so when we do that, we should get the orbital period. So 2 times pi times all right, so the period of its orbit is 6,182 seconds. We only have 3 significant figures, so 6.18 times 10 to the 3 seconds. It's what, just, what, an hour and 45 minutes? Something like that. Okay. All right, questions on that one? So the purpose of having you do that one is to illustrate the tricks that can be played on you in a satellite motion question. Okay? The key words to watch out for are height, altitude, above the surface. Okay? If it is asking for or giving you any of those numbers, the radius of the body being orbited has not been factored in or needs to be removed. They sometimes will ask you to calculate what's the orbital altitude. So you can't calculate that directly. You have to calculate radius and then subtract the radius of the Earth, whatever body is being orbited. Okay? Does that make sense? It's just one to watch for, because it's a dirty trick, but you got to watch out for it because they're always going to play. Okay? Or I'm always going to play because I don't have a lot of tricks in the bag. So, okay, let's have you guys try these ones. So number 2 is one of those ones that's going to require substitution. Number 1 does not, but they both give you kilometers and they both give you height or altitude. Yeah. Okay, so just be mindful of that. All right, give you a few minutes on that. Okay, so for this first question, the first thing we have to do is calculate the proper center-to-center orbital radius by simply adding the 359.2 onto 6.37 times 10 to the 6, okay, which is the radius of the Earth. All right, then obviously our other givens, even though they don't outright say this one, is mass of the Earth, kilograms, okay, and we're looking for its orbital speed. So we're going to say Fc equals Fg. They did not give us the mass of the International Space Station, and they don't have to because it's going to cancel. Right? So if we're looking for speed, we got mv squared over r equals big G times the mass of the Earth times mass over r squared. So mass of the International Space Station is going to cancel. We're looking for orbital speed, so we're going to multiply both sides by r. That r and that squared are going to cancel, and then we're just going to take the square root. So b will equal the square root of 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 divided by our 6.7292 times 10 to the 6. So if we enter all that in, we should get 7.69 times 10 to the 3 meters per second, but we'll just double check because they obviously use a slightly different Earth's radius than we do. So, yeah, we get 7.70, okay, meters per second. 7.70 times 10 to the 3 meters per second when we do it, and that's just because of the difference in the Earth's radius for us. Okay. All right, questions on the first one? All right, so on the second one, we have to do that whole substitution thing, because all we're told is that it's orbiting the Earth, and that it's orbiting at an altitude of 114,593 kilometers. That's really high. Okay, so 114,593 593 with 3 more zeros to convert it to meters, okay, plus 6.37 E6. Okay, we're looking at that number for our radius, and that's times 10 to the 8, 1.20963. Okay. Alright, so quite a bit further away. Okay, like what? That's a third of the way to the moon. Something like that. Okay, 'cause the moon's 3.85 times 10 to the 8 meters away, so it's, you know, getting there. We're looking for its orbital period, so we're looking for big T. Okay, now in this case, where we have FC equals FG, because all satellite motion is solved that way, okay, we're going to have mv squared over r equals big G times the mass of the Earth times the mass of the satellite, okay, divided by r squared. Problem is, we don't have v. And we're looking for period, which isn't even in that formula. So that's where we have to do this. V equals 2 pi r over t. So I'm going to square this whole thing, and I'm going to plug it in for v. So I'm still going to have mass of the satellite here, but I'm going to have 4, which is 2 squared, pi squared, r squared, over t squared times r. Okay, I just substituted in 2 pi r over t all squared, okay, into the formula. When I do that, this r and this r will cancel, okay, and now I can start manipulating to get t by itself. First thing I want to do is move t over there so it's on the top. So I'll multiply both sides by t squared. Okay, and then I'm going to multiply both sides by r squared. So r squared times r is going to be r cubed. Okay, and then I'm going to divide both sides, so my mass of my satellite's going to cancel, and I'm going to divide both sides by big G times the mass of the Earth. So this big giant mess that I've made here is going to end up being this 4 pi squared r cubed over big G times the mass of the Earth equals t squared. So if I square root that, I will have period.
Wouldn't it be simpler to find the acceleration due to gravity, and since gravitational force is the same as the centrifugal force, you would use AC v squared r over r to find v?
I don't think that's easier. No. But if you arrive at the same answer, okay. But this, we need to look at the fundamentals of satellite motion rather than do an algebra trick, right? We want to look at what are the things that affect period. Maybe a perfectly valid way to solve it, okay? Not saying it's not going to arrive at the right mathematical answer, but it doesn't look at it from a satellite point of view. It looks at it from like a uniform circular motion kind of point of view, if you get my drift there, okay?
Would we get marks again if we didn't use the substitution method?
How'd you do it without substitution?
I found speed by using the square root of g, mass of the Earth divided by radius.
G mass of the Earth divided by radius. Oh yes, you can do it, yes, in 2 steps, absolutely, yeah. Yeah. On this one you can do it in 2 steps, sorry. It's the other way around, where if you're looking for radius in a given period, you have to substitute. Okay, I like substituting. It looks cool. Okay. So when we do this, we're going to have 4 pi squared, okay, times our big radius that we calculated there, that giant number 1.20963, times 10 to the 8 cubed, so it's a huge number, okay, divided by 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24. So this gets pretty crazy with all of your cubes and brackets and all of that kind of stuff. Okay, so we're going to have 4 pi squared times, in brackets, 1.20963 E8, and then cubed. Okay, so that's the top, divided by 11, 5.98 E24, we gotta square root that. All right, so its orbital period is 418,547.9154 seconds. Is that what you got? All right, so we're gonna divide that by 3,600. That'll give us the period in hours, 116 hours. 4 days, almost 5 days, 4.8 days. So it takes a while. That one's pretty far away, and it is by necessity. It has to be beyond the Van Allen belts and all that stuff that can interfere with X-ray detection. Okay. All right, questions on that?
What's the belt you just mentioned?
Van Allen belts is basically the magnetic field of the Earth that protects us from all the really awful stuff that gets spat at us by the sun, including X-rays. So if you put this satellite beyond the reach of beyond the Van Allen belt, the X-rays can hit it and it can detect them better than after they've been deflected by our magnetic field. Because we don't want that stuff getting to the surface of the Earth because we don't need to fry.
I was just gonna ask what would happen if we didn't have that.
Well, if we didn't, more X-rays get to the surface, and I mean, you don't want to have too many X-rays in a year, right? It's not good for you. So imagine having a constant X-ray. Yeah, wouldn't be good. Probably be like a really bad sunburn, but like to the point where you melt. So generally bad. X-rays are very, very hard on living tissue, which is why they don't like to give you very many in a short space of time. Right? They'll give you an MRI or something else that doesn't involve bombarding you with shortwave radiation.
We would know if bones were broken all the time, and X-rays would be free.
Of course, your eyes would be burnt out, so yeah, there'd be that problem. It might go right through your bones, but that doesn't mean you'd be able to see through it.
Minor difference.
Sunglasses.
That are opaque.
Just use sunscreen. Just use sunscreen. You'll be fine.
It's not, yeah, polarized sunglasses are really not really meant to deflect X-rays so much, gamma rays and things that can turn you into the Hulk. So.
Just use sunscreen. You'll be fine.
Sure. You go there and you find the copper tone thermonuclear. That's the kind you need for that kind of situation. All right, I would like you guys in your notes, in your workbook package, I think there's 7 satellite motion questions. Just want to kind of get to work on those. I don't think it's going to take you very long. And then we'll start talking about gravitational fields after that. Oh, it's only 6. There you go. Try those 6 satellite motion problems. Okay, see how we do on those. All right, we'll go through any that give us trouble, and then we'll start looking at gravitational field strength. All right, so if we're trying to calculate the time of 1 year on Mars, okay, again, because I like to substitute, that's the way I'm going to do it. Okay, I'm just going to put in for FC that it's m 4 pi squared r over t squared equals big G times the mass of the sun times the mass of Mars over r squared. Mass of Mars is going to cancel, okay, so I don't need it even though it was given to me. And I just need to solve for big T. So when I manipulate this, I'm bringing big T over here, okay, I'm bringing the r's over there, so it'll be cubed, and then I'm dividing both sides by big G times the mass of the sun, okay, and then I'm square rooting it all. So big T will be the square root of 4 pi squared times 2.3 times 10 to the 11 cubed divided by 6.67 times 10 to the minus 11 times 1.99 times 10 to the 30. That's the mass of the sun. Okay, so once we plug all that in, we should get 6.0 times 10 to the 7 seconds. Okay, you want me to run through your calculator too? Any other ones, guys?
It's a lot of seconds.
It is a lot of seconds. It's 1.9 years worth of seconds. So you get a birthday half as often on Mars. So Mark Watney, I mean, it was all suffering for him, but he also didn't get a birthday
It's a scam.
as often.
That means I can
Yeah, relatively speaking. Actually, he won't. He'll die at a very young age because he'll only have a birthday every 2 years. Yeah. All right. If there's no other questions on the satellite stuff, then we're going to move on to gravitational field strength.
I think if you colonize the other all the time zones for planets, maybe they will all be Earth-based.
Okay. What's that?
Like if we go and colonize other planets, like how will we agree upon like Earth as a central time, or will we have that planet time zone?
I don't know. In Star Trek, they use star date. I don't have any idea what a star date is, but it is a centralized date system throughout the entire Federation, right? So they all use star date. I don't know whose star they pick for that, or if it's just a random, thing, but that's what they use. You would have to, right? Because everybody's years are longer. You can't say April 25th because, well, then maybe on whatever other planet there is no April, or it takes twice as long to go around its star. So yeah, I don't know how they would harmonize that. I mean, unless you just said, if I'm on Mars, I don't care what season it is, and I'll just go by the Earth year instead, right? I mean, that's what would match up, but if we're talking intergalactic or interstellar differences, I don't know. There'd be a lot of problems with that. Namely, I'm thinking communication. Yeah, by the time you get there, everyone on Earth who sent you there is long gone. Maybe, they're no longer waiting for a signal from you. Okay, so what we have to learn about here in terms of, we know how gravity works. Obviously, it's affected by the mutual attractive force between two masses and how close together they are. But gravity is a different kind of force from the forces we dealt with in Unit 2. Gravity is a field force. All of the other forces we've dealt with are contact forces. That means there has to be physical contact between the two objects for the force to be felt or even exerted. Field forces work differently. Field forces can be exerted even though there's no physical contact between the two objects. There is an area of influence around that object. The field forces that you'll deal with in high school are obviously gravity, magnetism, and electricity, because they all exert fields around themselves, okay, that can then exert a force. Anything caught in that field will be subject to a certain field strength. Okay? That field strength, at least for gravity, is measured as acceleration due to gravity. Okay? So the strength of a gravitational field is numerically equal to the acceleration due to gravity at any particular point. So the strength of the Earth's gravitational field right here is 9.81 meters per second squared, or 9.81 newtons per kilogram. Okay? That's the field strength measurement that we use. Okay? If I was to move further away from the Earth, I would be accelerating towards it less, because I would be further away from it, and its field strength is going to diminish exponentially as I move forward. Okay, everybody all right with that idea? Okay, so gravitational field strength doesn't look at this as a mutual attraction between two objects anymore. Now it's looking at it as the rate of acceleration of this object that's caught in the field toward the object generating the field. Okay, so it's now this on that, as opposed to they're together. All right, so it does change a little bit that way. Okay, so gravity is a field because it exerts a force without being in physical contact with another object, and gravitational field strength is numerically equal to acceleration due to gravity at that particular point. Okay, so is the moon trapped in the Earth's gravitational field? For now, yes, it is. Okay, that's why it orbits the Earth. Are we trapped in the moon's gravitational field? Yes, we are. Pulls on the oceans, makes tides. We're still inside the moon's gravitational field. Okay, there's a small amount of attraction towards the moon. I mean, it's not like it's pulling us off the surface of the Earth or anything. We don't have to worry about that, luckily. But okay, we are still certainly within the moon's sphere of influence. Okay, and we are within the sun's sphere of influence. That's why the Earth orbits the sun. The sun's influence is huge. Okay, it goes out well beyond Pluto, out to the Oort cloud, which is even further than the Kuiper belt. Okay, and there are things out there that are still gravitationally bound to the sun, loosely at least. Okay, if something else were to wander by, they might be more attracted to it, okay, depending on how big it is. And that's the kind of thing that can actually cause the orbits of Kuiper belt and Oort cloud objects to change and then cause them to fall towards the sun. Okay, which is exactly what they do. Okay, it's orbital, but it's still a fall towards the sun because of the sun's gravitational field.
Isn't like really technically every sphere's gravitational influence infinite?
Yep, technically yes, but it becomes so small as to be effectively not there. Yeah, I mean, you don't see, like, does the Earth, exert a bit of gravitational force on Jupiter and vice versa? Sure. Not enough to make any real difference at this point, because the Earth's field of influence doesn't extend that. I mean, it extends that far, but it doesn't have any practical effect that far. Okay. So, this was all Michael Faraday's idea. Okay, Michael Faraday, he didn't work with gravity, he worked with electricity and magnetism. Okay, but he was the one who took like a bar magnet and set it down on a piece of paper and then put a bunch of iron filings on there and found that it made this shape. Okay, so here was his bar magnet. Okay, so this was the north part of it and this was the south part of the bar magnet. And when he dropped the iron filings on it, the iron filings did this. They aligned themselves in the same shape and direction as the magnetic field of the magnet, which is exactly what Earth does. Okay? Earth generates a magnetic field around it that is exactly the same shape. Because it's got a north and a south pole. It's like one big giant bar magnet. Okay? And that magnetic field protects us from a lot of the crap the sun spits our way. Okay? If we have the northern lights, that means you can actually see the magnetic field of the Earth doing its job. Because what's happening is those high energy particles that the sun has vomited our way, because that's actually what happens when you have a big solar coronal mass ejection, a big flare. Okay, you've got a lot of high energy particles moving towards the Earth. Okay, and when they strike the Earth's magnetic field, it's like if you watched like a science fiction movie where they have shields and they're fighting. Okay, the shields kind of glow and light up. It's exactly the same thing. Our big shield that's generated by our magnetic field absorbs and deflects some of those particles, and when it does, those particles slow down, and there's light emitted because energy is lost. Okay, and so we see the magnetic field glow, and we see the auroras.
So every single Star Wars space battle is based off of the magnets, the shields.
Shields in all science fiction are some sort of electromagnetic field that surrounds the ship and protects it from matter and energy. That's exactly what our magnetic field does. It protects us from matter and energy, mostly energy, but a little bit of matter, okay, that's ejected our way from the sun. And without it, that stuff would all get to the surface. And that would be bad. Be like Mars. Mars has no global magnetic field anymore. It's got spotty little ones here and there, but no more global magnetic fields, and so everything just gets to the surface and it's irradiated. Your question, please.
So since does the magnetic field use energy to deflect the particles and all that?
The energy comes from the Earth's core spinning and being a big hunk of iron, basically. So there's this kind of dynamo that goes on there that generates this magnetic field. So yes, there's some energy. Some of it's from the decay of radioactive materials that have collected in the area, and the rest of it is the spinning of the core. The fact that it's iron just makes, like, iron is by its nature magnetic, right? And our magnetic field is pretty strong. It's pretty good. We're fortunate that way. Jupiter has an even stronger magnetic field. In fact, sometimes you can hear Jupiter's magnetic field on an AM radio. And if you just kind of, when you're in the static, sometimes you can hear it popping. You hear pop, 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 pop. It's actually Jupiter's magnetic field is actually that big. Okay? It's the second largest object in the solar system to the sun's magnetic field. Okay? It extends way out. Yeah, so, and if you're within it, It's actually so powerful that it emits radiation. Jupiter actually emits a fair amount of really hard radiation that would make it difficult. Some of our spacecraft have to be shielded properly from it, like they have a reflective coating on them, things like that.
So can we hear the sun's magnetic?
I would assume so. If we can hear Jupiter's, I would assume we can hear the sun's, but it's probably much more powerful. Like it's probably like the background static that you would hear instead. The popping is more because Jupiter's is much more regular, whereas the sun's is constantly. So yeah, you get these weird, I don't know if you guys have seen like videos of the sun where you can actually see the magnetic field lines kind of warp out when it's about to do a coronal mass ejection. Okay? It's this same shape, but you can actually see like plasma curl around because of that magnetic effect. It's really quite cool. Okay, so the idea of the field was discovered by Faraday, and then it was discovered that magnetism wasn't the only field force. Electricity makes a field, and gravity makes a field as well. So gravity is actually the weakest of the field forces. Okay, but it's based on mass, and there's lots and lots of mass. So it actually becomes the dominant, even though like per kilogram, it's the weakest. Okay, but because there's so much mass, it actually becomes the dominant one. Plus, its range is greater than the range of a magnetic field or of a electric field. Okay. And this idea of fields is also the reason why some people feel like you can't live close to power lines, you can't live close to cell phone towers and all of that kind of stuff because they make a magnetic field, and they do. But as we're about to see with all field strengths on the bottom have this. They're all divided by separation distance squared. So that means that further away you get, exponentially less effect of that field is experienced. So very quickly, the effect of a cell phone tower is diminished. Okay, and you know that if you go into a place where you're a long way from a cell phone tower, your phone probably doesn't work very well. Okay? The strength of that field diminishes quite well as you go away. All right, so the idea here that Michael Faraday came up with eliminated the need for all this other stuff people were talking about, which was these strings that extended through the universe and connected stuff, and that's how they were, these magical invisible strings, okay, that connected everything and kept things pulling and whatever. This made it that unnecessary, which they were also wrong. So the field idea made that make more sense. Okay, so if we're just looking at an object that's completely alone, its gravitational field lines will look like this. Okay, magnitude and direction. Okay, close to the center of the object, the gravitational field lines will be long and pointed towards the center. And the further away you get, the shorter they will be, but still pointed towards the center. Okay, that's if something is alone by itself. Okay, now this idea here, this formula, is really just this formula. Okay, just manipulated for G. But here's the problem. I've got to have this number. So what we're really doing is this. We're saying that at any given point, those two formulas are equal. Is that safe to say? It absolutely is. They're both calculating the force of gravity. They're just doing it in different ways. If I set them equal to each other, which is perfectly fine because they are, the smaller mass, the one caught in the field, cancels. Which should make sense in that all things fall at the same rate regardless of their mass. Okay, something we already know. Okay, so our formula for gravitational field strength looks like this. Little g equals big G times mass 1 over r squared. Mass 1 is always the larger mass. It is the one generating the field the second mass is caught in. Okay? Everybody with me there? So when we have this formula, and we're going G equals F over M, we get units of newtons per kilogram. Okay? And remember that a newton is a kilogram meter squared per second squared divided by kilograms. Okay? because it's only kilogram meters per second squared is force. Sorry, I was doing energy this morning in my science 10s, and we were doing joules, which are kilogram meters squared per second squared. Okay, so if we do this, a Newton per kilogram is still just a meter per second squared, yes? Same thing. Okay, so you can write either one, and it'll be correct. All right, everybody okay with that formula? Now, here's something you need to be aware of. This happens all the time on the unit exam and on the gravitation science. I ask you to calculate gravitational field strength, and sometimes I go as far as to put gravitational field strength in bold-faced, italicized, and underlined font. Is this the same as calculating this? It is not. This is the force of gravity. This is the gravity's field strength, or acceleration due to gravity. They are two different things, but what I see happen all the time is people do this. And they calculate the force instead of the rate at which they are attracted to each other. This calculates the force that's pulling them together. This calculates the rate they accelerate towards each other. Okay, and those are two different things, so just make sure you keep that straight. If a question says gravitational field strength in boldface, italicized, underlined font, it wants the first one, not the second. Okay, that'll ask for mutual attractive force or force of gravity or something. It'll use the term force. Okay, if it says field strength or acceleration, then it wants you to use the other. All right, so this diagram right here, this is the Earth-Moon system's gravitational field. What do we notice?
Moon's is tiny.
Moon's is tiny and the Earth's is
Less tiny.
less tiny. I was thinking warped. Okay? Instead of this diagram, where all the lines are uniform and they all point towards the center, here, the moon warps the Earth's magnetic field. Or not magnetic field, sorry, gravitational field. Warps its gravitational field because it has its own gravitational field. Okay? Oftentimes, gravitational fields or areas of influence are mapped in 3 dimensions and they look like holes. Okay? So imagine you had like some really thin rubber. It was all stretched out in a rectangle. Okay? If I put a bowling ball on one part of that, what happens to the rubber? It droops, right? It stretches because of the weight of that ball. Now, if I put a marble over here, does the same thing happen? To a lesser extent. And if I put it close enough to the big ball, it'll fall into it. Okay, so it's actually a cool comparison if you can visualize that. It's a good visualization of what we call a gravity well or a gravitational field area. Okay, so the moon is right here, and it has its own gravity well. But because of that, it warps the Earth's gravity well a little bit as well. If I put a bowling ball, and let's say, a shot put, okay, over in another area, it's not, quite as heavy, they're both going to make some dips in that rubber membrane. Okay, and that's exactly what these two things do to the gravitational area, okay, around them. And so you've got, a lessening here of the Earth's gravitational field, actually to a point where right here they would what?
Would they be equally attracted to the Earth and the Moon?
Exactly. Yeah. This is where the idea and where Lagrange points practically come from. They're areas of gravitational balance. Okay? Where if you could put something there, it would stay there. Okay? Just because there's no net gravitational strength pulling on it in those positions. So when you're trying to land a man on the moon, okay, and you're trying to get somebody there, that's something you have to consider. At some point, you're no longer trying to escape the Earth's gravity. You're being pulled in by the moon's. Okay? Now, it's obviously the balance point is a lot closer to the moon than it is to the Earth. Okay? Just because the Earth is so much bigger, you'd have to get a lot further away from the Earth before you stop being attracted to it, start being attracted to the moon. okay? But their fields overlap, and that's the effect of that overlap. All those vectors are warped and turned just a little bit.
So what are the practical implications of that if you're trying to go to the moon?
At some point, you're gonna have to start braking, or have some maneuver that allows you to bleed off some speed and be captured by the moon's gravity, because the moon's escape velocity is a lot less than the Earth's, and you're still moving at a velocity allowing you to escape the Earth. So you have to be careful. If you overshoot that, you'll just shoot right by the moon, and then what?
So how is there a Lagrange point on the opposite side of the moon?
There's, oh god, I gotta remember how Lagrange points work now.
Oh, there's.
Yeah, there's a whole bunch of them. There's L1, L2, L3. There's a whole bunch of them, and they're all based on the Earth and the Moon and the Earth and the Sun and their gravitational points of balance. I don't remember exactly. That's what I remember about Lagrange points. Yeah, I'll have to read that over again because it's been a while. Okay. I know of their existence and roughly how they work. That's roughly how they work. They're areas of basically null gravity. Okay. All right, everybody okay with that idea there? So are these going to be like really difficult problems to solve? And you're never going to set this formula equal to anything else. Okay, it's not like when we set force of gravity equal to centripetal force and stuff like that. This only does one thing. It calculates either the separation distance and gives you the acceleration, or gives you the separation distance and asks you to find the acceleration, and that's it. Okay, so that's all you'll ever use it for. It's a pretty easy formula and fairly easy concept. Okay, so so here's some of the kind of ideas here. So, oh no, that's mass and equatorial radius. Never mind. Okay, see if you can find the gravitational field strength on the moon, on its surface. So you're standing on the surface of the moon. Okay, you can use these numbers here. Okay, so we got 1.74 times 10 to the 6. Okay, and its mass, they're going to say is 7.35. We say it's 7.36, but it's fine. Just use their number. And calculate the gravitational field strength you would experience on the moon. Okay, so if we plug in those numbers, okay, little g is going to be 6.67 times 10 to the minus 11 times 1.74 times 10 to the 22 divided by 7.3. Whoops, I got that backwards. Got that backwards. 7.35 times 10 to the 22 and 1.74 times 10 to the 6, okay, squared. And if we do that, I think it comes out to about 1.6, yeah? 1.6 meters per second squared, or 1.6 newtons per kilogram. Okay, in any way, shape, or form, it's about 1/6 on Earth. Okay? It should be a lot lighter on the moon. All right, we'll leave it there for today, and tomorrow we're going to go over just a couple of other things and maybe start our gravitation assignment. I will hand back your circular motion assignments tomorrow. They're marked already. The marks are entered. We'll give them back to you tomorrow. I'm efficient.